right, AP Chem. Let's clear the board here. Some more chemical reactions. Pay no attention to that plane flying overhead. A solution of diamine silver 1 chloride, well, there's a mouthful, is treated with dilute nitric acid. Diamine silver 1 chloride. All right, this is a tip-off that this is a complex ion. We'll talk a little bit about that. You'll see some of these here. Look it up in the textbook. So, I've got silver. I know it has a +1 charge. Diamine has 2 ammonias. They are neutral. There's the complex. It has a +1 charge. So that's what we mean by a complex ion. Complex ion, a metal ion complexed with often ammonia, often hydroxide, maybe some other possibilities. Water is often a complexing agent. Complex ions are soluble in water. We've also got chloride. So this is really just an ionic compound in solution. And we're adding nitric acid. Now, nitric acid is a strong acid, so we're not going to worry about the nitrate part. Nitric acid completely dissociated. So that HNO3 is completely ionizing, to be most correct, into hydrogen ions and nitrate ions. Nitrate's going to be a spectator. All right? So we've written the reactants. Again, in these reactions, we are not including any spectator ions. Nitrate is definitely acting as a spectator. All right? All right, what's going to happen here? Key to this problem is a couple of things. Hydrogen reacts with the ammonia to form NH4. Okay, so let's just start writing some of these products. So I'm going to get NH4 plus. Okay. So the ammonia is converted to NH4 plus. This gets rid of the ammonia, and this therefore frees up the silver. Okay. And therefore, we're going to get silver ions and chloride, and from your precipitation rules, you know that you're going to get silver chloride, a solid. Again, do not need to include state designations, but the formation of the solid here is an important part of this reaction. All right, so you get two things going on here. The hydrogen ion is reacting with the basic ammonia to destroy the complexing ion. This releases the silver ion free into the solution, where it is able to act with the chloride to form the precipitate. So the next question, what is the driving force for this reaction? Well, I really think there's two driving forces here. One driving force is the acid-base part, ammonia reacting with H plus to go to NH4 plus. The other part is the precipitation of silver chloride. So in terms of driving forces, they are both driving forces. I suspect if you would put either one of those, you would get credit. All right. What type of reaction is this? It's got a little bit of acid base. It's got a little bit of precipitation. It's involving complex ions. All right. So it's got a number of different categories you could put it into. All right. Let's go on to the next one. A concentrated solution of ammonia is added to a suspension of zinc hydroxide. Suspension is just a solid that's been a heterogeneous mixture, solid solution, solid liquid that have been mixed up really well. So suspension. Okay, if you let that suspension sit, guess what would happen? All of the zinc hydroxide would fall to the bottom. So a concentrated solution of ammonia, again, reacts with zinc hydroxide. An insoluble substance. Okay. Again, this is looking upstairs, the last reaction. In that high concentration, notice they said concentrated, okay? The zinc becomes complexed by the ammonia. The number of complexing ions is complexing molecules is often 4. So we get the zinc tetraamine complex. Zinc keeps its +2 charge. It's not changing its charge. +2, and the 2 hydroxides now go into solution. So essentially what the complex does, if we were to add this, okay, if we were to observe this, we would see the suspension, okay, the whitish zinc hydroxide suspended in that environment. As we added the ammonia, as the ammonia concentration got higher, we would see the zinc hydroxide go into solution as the complex ion, zinc tetraamine, and hydroxide. So we would see the mixture go from a white, powdery, milky substance to clear. Maybe I'll do that as a demo in class. All right. Let's see. What are the possible molecular geometries for the complex ion product? Notice that there are 4 things. Around that complex ion. When we think of 4 things, I hope everybody thinks tetrahedral. That's one possibility. Okay. Another possibility when you have 4 things is a square planar arrangement. Either one of those would definitely get you credit for that problem. All right. So again, putting down something logical, something reasonable. Again, when you're writing the reactions, keep in mind that if you can't write the products, at least try to get the reactants down. That'll get you some partial credit. This reaction, I'd say this one mostly complex ion. Okay. Good. Boy, we're on a string here with complex ions. Next one, notice the similarity here. Concentrated sodium hydroxide solution is added to solid aluminum hydroxide. So again, sodium ion, always going to be a spectator. Okay, so we're just going to write the sodium hydroxide as OH minus. We know sodium's always going to be a spectator. Reacting with aluminum hydroxide. Be careful with writing the formulas for those ionic compounds. Why aluminum hydroxide? Just to review, aluminum is a +3. Look at your periodic table. Hydroxide, one of your polyatomic ions, -1. 3 aluminums to 1 hydroxide. Again, that is a solid. You don't need the state designations. Now, under the concentrated hydroxide, we form an aluminum complex ion. Another hydroxide comes in, and suddenly we form this aluminum tetrahydroxide complex ion. Notice each hydroxide a little different than above. Since hydroxide has a negative charge, the 4 hydroxides complex with the aluminum. The aluminum keeps its +3 charge. The overall charge on this complex ion is -1. Okay, so there's our complex ion. Often when we write complex ions, we go ahead and put a bracket around them. Not necessarily essential, but helps to clarify. So there's the complex ion. The complex ion brings the aluminum into solution. So whereas this is a solid, this is going to be in solution aqueous. Name any complex ion formed. You would name this as the tetrahydroxide aluminum complex ion, okay? Or some people might call it tetrahydroxy aluminate. I have to believe that the graders would be pretty liberal here. They're going to see the tetra here. Again, tetra is the standard prefix for 4. So tetrahydroxy, hydroxy referring to the OHs, aluminate ion. Okay. I'm also thinking that tetrahydroxide aluminate would be fine as well. All right, last one. Solid ammonium carbonate is heated. All right, we'll go back to this one. This is another complex ion, first of all. Complex ion. Finally, ammonium carbonate is heated. Notice no other reactant is given. This tells you this must be a decomposition reaction. So first thing, be able to write the formula. Ammonium carbonate, ammonium polyatomic ion with a +1 charge. I'm going to need 2 of those to balance the carbonate with a -2 charge. Again, ammonium, NH4+, carbonate, CO3, 2-. Boy, you do not want to lose points on easy formulas of ionic compounds. Heated. Use that little triangle sometimes, although that's not necessary. Always an indication that you've got a decomposition reaction. And now you're looking around and say, what could this decompose to? And you say, well, ammonia looks like it could be a good thing. Water and carbon dioxide. So this ionic compound decomposes into 3 covalent compounds. All very stable covalent compounds. In order to balance things, I think we need to put a 2 there, and that balances everything. So ammonium carbonate, which is the solid, decomposes into ammonia, water, and carbon dioxide. All right. So looking at a couple of things. Carbonates, fairly unstable. Under heating conditions will often decompose. into carbon dioxide. Ammonia, ammonium compounds, again, when heated, decomposing into ammonia. All right? And this is definitely a decomposition reaction. Decomposition. One thing going to many things. All right? Are we good? All right. Super. Decomp. There'll be more.